Okay, it's 1:30. We're gonna get started. So did anyone think about permutations? Did anyone have a dream about rearranging yourselves in a room? Did anyone black out and forget everything that happened? So I figured you might. So we're gonna re-review, because studies show that if you really want to remember something, you're supposed to learn it and then relearn it the next day and then relearn it in the same week. So every day we're going to go over what we did the day before. So what do we talk about? We talked about the fact that all the statistical tests you use are derived from calculus and these theoretical distributions that, if you look precisely at any data set, don't match up. We just sweep it under the rug, and it's close enough sometimes. They usually assume that your data are normally distributed, so you do these fancy things to transform your data. We're not biased creatures, so we usually pick the best transformation, and then we run the tests. So what I wanted to show you is a little bit about probability and statistics, and a little bit about how you could actually think about what that means and run one single test for all the things that you want to do. So we talked about why we collect. Maybe the important thing is that no one cares about your data. You care about the statistical inferences that you can make from your data. You care about this. You want to compare those two things. That's fundamentally what we're doing in science. What's true between genes, not just what's true between genes in your sample. Those are the population distributions. You don't observe them. We talked about how every time when you do a test, implicit when you say, is there a difference, that we don't say out loud, there's some way you're comparing things. You compare the mean, you compare the median, you compare the ratio, anything, but that's a test statistic. Every test has one. It just goes unsaid because everybody loves the mean because it's easy. But as we showed and we learned in our example, by switching out mean to median, it's not always the most powerful. So you might be leaving statistical significance on the table because you didn't use the right test statistic out of convenience. We got an order of magnitude more significant in our salary comparison. When we talk about, what does it mean to do statistics? Well, one thing is it real? And we talked about that being, it's easy to know what the difference is between your two samples. If you have a group that didn't vape and a group that did vape, you can calculate changes in lung damage or lung issue reporting pretty easily. And then the question is just, well, maybe that was just noise. So the hard part is figuring out what would be possible due to noise. And so what we did was, instead of guessing, we can literally just do it. And that was what the permutation test was, which was, we take our exact salaries, the exact same ones, and we say, look, let's imagine we observe the same data points, but we enforce that there was no effective group because we just shuffle. And every time we just redraw the numbers and fill our two different groups with these fake sets of numbers. It's the same numbers, but sometimes they're UCLA, USC, you just flip a coin. So we flip coins and said, oh, well, even if we flip coins, we still get random differences. And then what we end up finding is that, well, if you look at them all together, most of the time you get no difference because it's all shuffled data, right? You just made it up. What could have happened due to random chance? Usually nothing. Most likely no difference, but sometimes big extreme things. And all you do is then compare where you are relative to those 10,000 simulations that we did in the code. So the code just flips a coin for each sample and randomly assigns it to a group. So you have the same data, but there's no effect of the group because you enforced there was no effective group by shuffling it. Flip a coin, flip a coin, flip a coin, flip a coin. And that's how you end up telling what could have happened to a chance. And then the p-value becomes pretty obvious. It's like literally in your simulations all the time, your little fake shuffle data turned out to have a bigger difference than the real effect that you observed in real life. Which is kind of crazy to think about, but it's just reminding us that our data are one way it could have turned out, and it could have turned out like this. So that's the p-value. It's just all the times chance was actually bigger than what you even saw. All the times that you would have been wrong. So then we went through some examples. We talked about the most important thing out of this was just the p-value is just look, if we think there's nothing going on, if there really was nothing going on, and I don't know the truth, I don't know if vaping causes cancer for sure, maybe it does. But if that was true, how likely would I see this big difference between my groups in cancer rates? And that's what we're quantifying, right? That's another way of looking at that p-value right there. It's all the times that we shuffle the data and we still found an effect. So the probability that you get this extreme data given there really is nothing going on. It's like a false positive. We looked at that, and then we started to introduce the bootstrap. We didn't complete it, but we will today. And with the bootstrap, remember this first part, the permutation test is the shuffling. That's about whether something's real or not, the significance test. Is it true or not true? Is there any meaningful difference, yes or no? And the bootstrap is about quantifying uncertainty. It's, oh, well, yes, there's a difference between vaping and not vaping that causes cancer. And it's 12% plus or minus 1%. That's a different thing, right? Just because it's true doesn't mean it's big effect. It might be 0.001%. So you report some number, but you got to show how certain you are in it. Or the correlation between the number of times you vape and your cancer rate is 0.2. Well, like, how certain are you? 0.2? Maybe, could it be 0.1? Could it really be 0? Could it be 0.9? Could it be really high and you just didn't have enough data to tell? So the bootstrap that we're finding out was all about figuring out uncertainty. We want to figure out this. How sure are we in our measurement? And so the salary data, it's the mean at our sample is 64K. But if we want to make an inference about what's true that we don't observe, it could be a little less, it could be a little more. And we talked about what's the idea behind the bootstrap is just, let's just pretend that the sample data we got is good enough to reflect the true population. Like the general shape of how many people earn how many salaries is pretty much right. And then you can sort of just roll the dice. But like, let's say we had a dice with each sample on a side. You just roll it, and each time you would draw the same number of samples, 70 again, and you'll get a slightly different data set. But you're saying, you know what, maybe my experiment could have turned out that way. Could have turned out a little bit differently each time. And then when you do that, you roll this dice over and over again, you get a different mean each time. Here's a mean, here's a mean, here's a mean. So you don't have to guess about standard deviations or anything. You literally just do it. Take your data, use the code, and you'll get, here's all the means you actually observed by shuffling your data and bootstrapping it. Most of the time you get 64K, sometimes you get 60K. So that lets you know how certain you should be because you literally did it 10,000 times. And if it never showed up to be $100,000, it's probably really unlikely that the true salary mean at UCLA is 100K. 64K, yes. 63K, yes. 70K, maybe. 100K, didn't see it one time. So what we're going to do now is we're going to get into the code that I wrote and hand it to you guys. And just so we're clear, what I wanted to make the point here is none of this is crazy. Like you're already doing this with when you do the 1.96 times the standard deviation divided by the square root of the number of samples you got, like the standard error of the mean calculation. You're already doing it. You're just assuming that it's normal. You're fitting a normal curve base. So you take the mean and you do plus or minus the standard deviation. So you're already doing that. So we're not asking you to do anything different. We're actually, remember, in all these cases, we're making fewer assumptions. This is parametric statistics. It's the assumption that it follows, parametric means it follows a distribution. This is non-parametric. We didn't make any assumptions. We let the data, we just change the data and let what happens falls out. And if you do machine learning, this is the way to do it. Especially if you do machine learning on your data, you want to predict one outcome versus another. You don't really have a good formula for what should or shouldn't look like. So you literally just take your data, scramble it or shuffle it, and just figure out how well it performs by chance. Or how certain you should be in your metric. You just scramble the data. So this is what I like. You basically, because you have computers, you start with your very first principles, your data, and you just make modifications there, and then you let everything else propagate out. And all your results just propagate out. Change the metric, you can do ratios, medians, means, all that stuff. So the point here was we didn't make any additional assumptions. So then we went over some glossary terms, but we don't need to do that again. So what I want you now to do is open up the one sample magnitude bootstrap example in RStudio. And that is one sample bootstrap.rmd. It should look just like this. And we'll go through it. So when you hit knit, oh, and just to be clear, in all these examples, since you don't have a virtual machine, you need to just, whatever you changed this path to before that made it work, you got to change it again. So it's got to read in the right data file. So if you just had to change your username because you use a Mac and you downloaded it in the downloads folder, you just need to change this before. Whatever you did, just copy it and paste it here. You do the same thing. And if it's in a PC, I sort of commented in here what I think it would be. And this # just means it's text that you read. The compiler doesn't actually interpret it. So it's not real with a #. If I do this, now it's real. See how it changes colors? It's called a comment. All code languages have comments, so we can, because we're not machines. So when you do this, here's our data. And we do basically the same thing we did before. We take our, what's the actual mean of my salary? Let's say, what's the actual mean of my USC salary? Okay, so that's what I really observe. I think it's like 70K. That's my best guess. But when you have to put confidence bounds on it, you do this for loop again, and the only difference is you sample again, and you get these bootstrap salaries, and then you take the mean of it and you store it in a bucket each time. Each one of these loops goes from 1 to 10,000, and each time it goes into one of those 10,000 buckets. So you store it, and then at the very end, we'll plot it all out, and those are these values right here. So the mean value of a salary at USC is 80 grand, according to the data. And I'm 95% certain it's between 72 and 89. That's it. And I'll just explain that last piece. And I printed some of them out here. So when I do my bootstraps, here are, I sorted them. So I did 10,000 times, right? And I said each time you get a different, yeah, please. Yeah, absolutely. Let's see if that works. Yeah, thanks. Anybody having visualizations with this or anything but seeing it? Okay, cool. Visual problems. Just can't see it. Fine. Totally fair. So what I did is I sorted all this because you'll get 10,000 random salaries that you could have got if you reran your experiment. And I sorted them and I just printed them out so you can see. So when I reran the experiment one time, when I resampled my data, it's called resampling. I happened to get a lot of the low numbers, so I got a low salary. And some of the times I happen to get a really high salary. So I got a high number. So I'm just printing them out. This is what those 10,000 buckets look like when you sort them. So if I just sort them in order from shortest to tallest, let's say, and you walk in 2.5% and 97.5%, then you get 95% of the data will be in the middle, and those are your cutoff bounds. And that's how I calculated these blue bars right here. I just literally lined up all my sample in order, and I just said, well, what's the 250th sample and the 9,750th sample in order, and that'll give me the middle should be 95%, right? 2.5% on each side, 95% in the middle, and for whatever reason, our confidence intervals are always 95%. We like that number. 1.96 is the number of standard deviations that corresponds in a normal distribution to enclosing 95% of the area. So that's what we do. You don't always want 95%. If you care about a test diagnosing, let's say, a form of cancer, and it will be the last test until there's an operation, I might want a 99% confidence interval. I might want to be really sure. And so you could modify these values right here. So if you look at the code, it ends up being pretty simple. You basically, what did I really see? What happens if I resample my data and try and look at the mean? I get a whole bunch of different numbers that look like this. Each time it's a little bit different when you rerun your experiment because there's noise. You just got some sample of data. If you reran it again, you'd have a different number. And then you just look at it. Now, a lot of the examples we've used so far, yeah.
Does this work with like fewer samples?
Yeah.
How many samples do you want?
Any number that you would use for calculating a confidence interval normally. Because like I said, you're making the same assumption. If you only have 4 points, hopefully now you understand that when you calculate the mean in the confidence interval, you are assuming there's a normal distribution centered on that sample mean, and it looks like this. And you just happen to get 4 points in that. So if you would do a normal test, you could do this. Mm-hmm. And in this case, we're not. So, okay, so maybe in the back of your head, so today's the day where you start to see some more payoff, which is like, okay, you can do this already with the mean, who cares? So then I want to do before I move on, sorry, is there any questions on this, on the bootstrap? And you just remember, it's not centered at 0. This is When I report the magnitude of my effect, I care about the bootstrap. It's how certain am I in the magnitude? What is the cancer rate? Not does it cause cancer? Okay, it causes cancer. How much? Okay, this gene variant is linked with Parkinson's. True. How much? Does it give me 1% more likelihood or 100%? And how sure are you? What's the correlation between height and weight? How sure are you? All these things. You always, whenever you see those little brackets on papers that put the confidence intervals, that's what we're talking about. And what this will allow you to do, and we'll see today, is you can put confidence intervals on things you never would put confidence intervals on before. Yes?
So you're writing a paper on salaries and you have a p-value and you track your.
I think I know where you're going.
How do you write this into your paper? How do you write it?
Between condition A and condition B, we observed a mean effect magnitude of X, 64,000, confidence interval 55 and 72. This effect size was significantly or not different from the null hypothesis, P less than, well, P equal to or less than whatever your P value was you got here. 2 sample percentile permutation test, because that's what we did. Thank you. Great question. And I just want to, it's simple to ask yourself, right? These are two different things. They might seem like the same, but you can have a true effect that it's really small. Like if you drink 9 gallons of water every day, maybe it increases your risk of cancer by 0.0001%. And somebody did that study. Sure, it's not, it does have, there is clearly an effect there. It's just really small. So we all know those, when it frustrates us, right? Maybe it just frustrates me. You see those papers come out and they find an effect, but it's like when you look at the paper, it's tiny. This, the smiling pen effect. If you hold a pen in your mouth and you smile, then people report themselves to be happier the next day, or right after that. Sorry, right after they do this exercise, because you're smiling and it's embodied cognition. But the effect size, it's tiny. It's like a boop, little baby effect. Sure. So true, first level of understanding. Next level of understanding, how true. How big? So that's what we're talking about here. Magnitude. How big is your effect? You bootstrap it. We just showed you that. You quantify the uncertainty on your test statistic with confidence intervals. Bootstrap goes here and only here. This is super easy. You can calculate the mean of your distribution or the difference between your vaping and non-vaping samples in 2 minutes. That part's easy. But the confidence intervals, how sure should you be? Should it be the cancer rate's 10% plus or minus 1%, or 10% plus or minus 8%, because you're really uncertain? It matters. And then the second question, which might be in your heads go first, though, is, well, is there anything real here? Is there anything different at all in the first place? And so you can have things that are true that have small effect size, and you can have a small number of points and find that, oh, there's a huge difference between condition A and condition B, but you don't have enough data to show that the p-value is low enough to be true, right? So you can have a big effect, but you haven't discovered it's true yet. Or you can have something that's true with a small effect. And that's why these are 2 different things and there's 2 different tests. Bootstrap to quantify uncertainty, permutation test to ask, well, is it real? So permutation test usually comes first.
And I'm sorry, I missed the point where you get the effect magnitude. So how do you get?
You would just, for the salaries, you would just mean of the vector.
Oh.
That's the easy part. It's so easy, you're probably not even thinking about it. If I asked you what's the salary difference between USC and UCLA, you just just subtract the 2. So that part's easy. But how, yeah. So that part's like the easy part. We often overlook how easy it is, but how certain should you be is the hard part. Great. So, yeah.
Quick question. Repeat your questions if you could restate the question for the folks.
The question was, I don't have a good short-term memory. The question was, how do you calculate the effect magnitude? And the point is, that's the easy thing. You just call mean, or whatever your effect is, mean of UCLA salaries minus mean of USC salaries. You get a number. That'll take you 30 seconds. Sure. So we did our example. Now what I want to do is so this is our conclusion. Now I want to ask, I want to do an assessment. So I want you to take this code, and I want to give me what's your best estimate for the median of the population distribution of salaries. So this is quick. Don't overthink it. This should take a minute. Take your code. I'm going to give you 2 minutes, and you're going to tell me what you think the median is with confidence intervals. And if you have any questions in getting your stuff up and running, now would be a good time. So take your code, open it up, and I told you the mean. I want to know the median.
There's a question from online. Suppose in the method section of a paper, would it be acceptable to say that the 95% confidence intervals were calculated by a bootstrap, or is there a more formal term to say that?
That's sufficient. That's what I put in my papers. Okay, who has an answer for the median and confidence intervals? A little louder and slower, please.
74,730.
Okay, and what was the confidence intervals?
70.19 to 81.
Okay, 70.19 to 80, 81. Cool, interesting. So not symmetric, as you might expect. Does anybody else get something similar or different? Yes, I got something similar. Yeah, okay, great. So let's, we'll do a quick summary and then we'll move on to a slightly more advanced example. So all we're still, we're confidence intervals. So in your head, you're like, oh, bootstrap. Confidence intervals, bootstrap. So all I asked was to change the metric now. Instead of doing the mean, I'm getting the median. So I'm switching that out. So I have to switch out 2 places because I didn't make it super complex for y'all. But okay, so what's my true median is here. And then each time, once I draw my bootstrap samples, rerun my experiment, make sure you take the median each time. So it should be just that easy. We'll pop it out. What do we get? Okay, did it look like that for you? Yeah, it looks ugly. Remember, the median is like an insanely useful metric that's underutilized, but it's filthy to play with. So that's why we don't do calculus on it. So this is what it looks like. Non-normal, won't get normal. Doesn't matter how many bootstraps you do, but you now see that it seems like roughly I got the same numbers as you. Yep, there's 71 or 70 point whatever. So this is what you do. So you just swap that out. That's pretty easy. Okay. Did we feel clear on the bootstrap? Just put an uncertainty on it. You can imagine, as we'll do later, we could do with correlation. Just run your correlation every time. Bootstrap it. That's it. So what I want to do is do one more test. I want you to pull out, so we can distinguish a bootstrap and a permutation test. Pull out the permutation test we did yesterday, the unpaired example. Looks like this. And now, so we can sort of start to see the power of this, I want you to, instead of taking the mean or the median, I'd like you to calculate the ratio of salaries. So maybe the difference between schools isn't an additive effect. Maybe private schools don't just pay people more money, but they pay you a percentage more, right? Sometimes our effects are not additive, but multiplicative. They pay everybody 10% more. Maybe that fits the data better, so maybe we should try that. So now I want you to take this and tell me, answer the question, is there a significant difference between the salaries of USC and UCLA as measured by a ratio? By raise of hands, do we know off the bat what traditional parametric test we would use for this? Perfect. Great, so let's try this version. So what is the ratio of salaries between the universities, and is it significantly different from chance? I'll give you a hint that it's not a lot of changes because the method is the same. Let's do 30 more seconds. Does anyone have an answer for this? Does anyone have the ratio? Was it significantly different from chance? Raise your hand if you have an answer. Okay. Do you feel comfortable saying it?
I got the objective 6.4%.
Okay. And was that, I love it. So the effect size was 16.4%. And was that significantly different from chance?
P-value was 0.016.
So we would reject the null. Yeah. Okay. Because less than 0.05, so we would say that's significantly different from chance. Great. Did you get a similar answer? Okay. Do you want to say it out loud?
I guess I did observe.
Okay. So 25%. Yeah. I have a suspicion of what you guys did differently. Which 1.25 or 1.16? Okay. And it's funny, whoever got it wrong, it's actually a prelude to what we're going to do in a second. So you're ahead of the game. Okay, great. So let's check this out. So what did I ask? So I'm asking first, is there an effect? Is it real? Trigger for you. Oh, permutation test. Shuffle, shuffle, shuffle. Because I can simulate what's not real. So you open this code up and you're like, okay, what's my statistic of interest? It's no longer the mean difference. My statistic of interest is now the ratio of salaries. So each time where I was calculating the median difference or mean difference before, I now want to calculate, take what's my average salary and I'll divide it by my average salary in the other group. So the mean salary at USC divided by the mean salary at UCLA. And if you did the division first and then you did the mean, you're making an additional assumption that we'll talk about later. But this is what it is, right? Whenever you have two groups, if you want to say what's the ratio, you just take the mean of both, and you could do a median ratio, by the way, too. if that, again, captures your data better, that what's the change in the median income between countries, you would just, instead of doing the mean, you would do the median here. And you don't need to look up a crazy distribution because nothing changes about our method. You're totally welcome to do that. That's the wonderful power of it. All right, so take the, for in this case, we want the ratio of the means. So my mean salary at USC divided by my mean salary at UCLA, and I'm just signifying that USC comes first in both cases and checking that's right. This is what I literally observe in my sample data, and this is each time when I randomly shuffle the data, what I would have gotten by chance. So I'll get some distribution, and we should be able to tell here that on average, this should be, I think, centered around 1. Right? Because on average, the ratio of the salaries, if it's shuffled, should be 1. So on average, just by noise, I should most of the time get 1, but sometimes get a little less. Sometimes I get a little more. So then I hit net. And that's not what I should, yep, hold on. Yep, I don't need to walk through anything. You've seen all this code. So I have an observed effect size of 1.25, and the p-value was 0.007. So maybe the mean, you know, that was more significant than our original additive difference. So we did a ratio, maybe that was the right one. And the histogram you get for the ratio is here. I have my confidence intervals here, and I have my effect size, which is here. So this would have been my 0.05 cutoff. But here it is. So here it is, and all these times, these little white bars, what are these again? Where are all these little white bars to the right of the green line? That's the p-value. All the times when I literally shuffled my data, I got an effect more extreme due to random chance. So I can't say that my salary effect sect is for sure true, but the p-value is pretty low. It's not consistent with, the data aren't very, very consistent with there being no difference between the universities. Just want to get that memory. Just if you just think about it this way, you can always think the p-value is all the null distribution to the right of your effect and to the left, but we're not dealing with that. Okay, so that's what I got, and we'll answer your question. You already have the answer to the next problem, actually. Any questions here? Okay, so you know what? One thing I might want to look at, just because we can, let's change it from mean to median. So I want to know, are the median salaries different in some ratiometric form at these universities? I have no idea if there is a test for this, a traditional test, but I'm just going to simulate it here. And again, this really matters when you have skewed distributions, but you want to compare them somehow in a meaningful way. It means the wrong metric and not valid. But if I do it to median, let's see what I get here. Taking some crunching, doing a lot of hard work, breaking my computer, but pretty fast. Okay. So again, we get a pretty messy distribution, but we find that our p-value is now really, really significant. So what I didn't tell you is I actually only had the UCLA data, and I just made up the USC data. And I thought I was making it up randomly, but in my head, I probably had a bias to do some ratio. So I did a ratio. I increased all the points randomly and got a ratio. And so the best thing that encapsulates what happened is a ratio of the medians, because it's this skewed distribution. So we're like, hey, so now you say, yes, there is a significant difference in the ratio of median salaries between USC and UCLA. Permutation test. 2-sample percentile permutation test is what we did. P-value 0.00053. So now we were able to look through the use of the right metrics, because we're not confined to doing mean anymore. We saw it changed in the p-value from being 0.01 to being 0.00053. So if that doesn't tell you that how you choose metrics matters for your data, I don't know what to tell you. It matters a lot. Right statistic for the right test. So I think we're going to skip this because there's more interesting things to say, but this was the summary here, and this is how you put it in a paper. Between condition A, we observed a mean effect magnitude, or we observed a ratiometric magnitude, or we observed a ratio of the means, a median effect magnitude of 17% or whatever it was. Just say what you did. This is what I measured. Here's the size of it. Here's how sure I am. This was significantly different from the null hypothesis at this level. So you do both the bootstrap and the permutation test. That's it. So you can check out the slides. You can look at it. P-value is the permutation test. I remember permutation, it was just an ordering of things, and we always shuffle the order. But today you're in a different permutation than you were yesterday when you came in. You all sat in slightly different seats. Weren't you? You were over here. Now you're here. So, you know, different permutation. So that's what it is. You're just ordering. And all a permutation test is just shuffling your data. All right. Nope, did it. We don't have to do that. We don't have to do that. So what I want to talk about is the paired data. So someone pointed out correctly yesterday, it was called unpaired data, and that was intentional because paired data is something else. Paired data is linked. Paired data is, what's an example of paired data? How about that? I got one yesterday about before and after. What else could be paired data? Does anyone have paired data that they use? Yeah. Perfect. Pre and post. I came in at 150 pounds and they shot me up full of steroids and now I weigh 160 pounds. It's the same person you're measuring twice. There's anytime when your outcome variables are linked. Same thing you're measuring, but they're linked by the sample. If the same professor went to both universities, now we have more information about their salaries. And can someone tell me why that matters? Why do we care that we have paired data? Do you ever look at what happens inside a t-test when it's paired data? What are they doing? Oh God. Okay, so paired data with a t-test, if you look at it, all they do is they take your samples and they just subtract them. And then they run then you have all your points. All you care about is the changes. Why is that helpful? Because ideally we love paired data. Why do we love paired data so much? So hopefully you guys can see this online. But let's say that somebody comes in to my, sorry, do you need this, Alex? Let's say somebody comes into my crazy, while this is happening, please sign in. Let's say somebody comes into my crazy science experiment and continuing with your pre-post example, let's say they come in at 200 pounds and we shoot them full of steroids and they leave at 210 pounds, right? So let's just say this is the axis for weight. They came in at 200 and they left a little bit higher at 210, all right? 10-pound improvement. Now let's say somebody else came in at 100 pounds and they left at 110 pounds. Let's say another person came in at 150 pounds and they left at 160 pounds. So if you look at the data and you didn't know they were paired, if I just had 3 samples of people pre and then 3 different people who came back later, and you compare these distributions, you can tell it would take a lot of points to show there's something that's different here, right? They're like almost overlapping. But if you know that the data are linked, you can account for the fact that people and samples and things have intrinsic properties that mean they start at different places. So you can tell that everybody gained 10 pounds. So there's clearly an effect going on. And if you had 5 samples, it would be very significant. But you're subtracting, the 200 pounds and the 100 pounds are now dissociable and interpretable. So you're basically subtracting and ignoring that. So when you look at the data, instead of looking at a whole bunch of sample points, let's say here and here, here and here, that show, again, that probably wouldn't be significant. They look like almost overlapping distributions. But if I plot instead, if I were to plot for you what are the differences, and this was 0, or this was 10, and this was 0, they would all be up here. You'd have a whole bunch of points, and chance would be around here, and you'd have a very significant result. So what matters is the improvement or the change between condition A and condition B, and because you know something about that sample, you get to parcel out what's called some of the intra-subject variance. You care about that. You care about how something changes from condition A and B, and you can subtract out this part. So when you pass a new t-test, you can look. Next time you call MATLAB and you call t-tests, it does this. It'll be the same example as if you just passed it one vector in with all the differences. So it's caring about, hey, is this different from 0? That's all it cares about. So same data shown two different ways will get different results, and we're actually going to do that and see it. I see a chat. Yep, thanks. Okay, great. So let me share my screen again. So paired data matter. So let's talk about, does anyone have a question? I mean, the most important thing, the functions are ready to go. So the most important thing is, are you going to leave here understanding what a p-value is, how to do multiple comparisons, corrections, and what it means to have things like paired data. Like, these are fundamental things that'll follow you. So there's packages for resampling in R. You don't need this. So do we get why paired data matters? And we can visually get that's not a significant result, but that is, given exactly the same data. So you have to know linkages. All right, so how to sample link data. So let's say we have a bunch of fish, and I measure their length on day 1 and day 7. Here they are. There's the fish. If you were to actually plot that data, because that's important, you'll show that I just doubled all of their length. Just manufactured this data set. If you were to compare them without knowing that they were linked, you might say that fish on day 7, or if I asked you, are fish on day 7 longer than day 1, and I didn't tell you they were the same fish, you'd have one answer. If I told you were the same fish, you can see that every single fish gets longer. It's a lot easier to see these significant effects. That's why we care about paired data. Always pair your data if you can. All right, so here's how we might sample it, which is, if I were to say, hey, is there something real going on? And we talk about, oh, you just shuffle everything and redraw your sample sizes and see what happens. Now you have a little bit more information, which is, and this is going to get a little technical, a little bit, so just listen. For fish 1, if I want to say, hey, is there a significant difference in the length between fish on day 7 and day 1 of their life, because they're still growing or not? What you're saying is that, okay, I'm clear that fish 1 had a measured length of 4.07 and a measured length of 8.14. We're not saying anything about that. We're not going to shuffle everything. I'm going to say it's totally random which day it showed up on. Because if there really was no effect of day, then it's by totally random chance that 8 ended up here and not here. And this fish, I'm clear that fish 12 had a length of 10 and 20. I'm just saying it was by random chance that 10 ended up here. It could have ended up here just as much. That's the null hypothesis, right? There's no effect of day 1 or day 7 on length. No effect. Same with schools. If it was USC and UCLA, and I knew some professor made both these salaries, random chance. They actually could have flopped the other way. They just happen to make a salary because they're a professor. They make about 120 grand, maybe 140 in whichever university ended up at. No big deal. No matter, right? That's our information. That's what we're clear about. We didn't lose our records. We know that this length belongs to this fish and not this fish. Did not forget our paperwork. We're just saying there's no effect. So now we're starting to uncover that really what it means to have a permutation test is it's a few steps. Like, what's your hypothesis? There's a difference between fish length on day 7 and day 1. Okay, what's the opposite of your hypothesis? The null hypothesis. So there's no effect of day on length. Okay, prove it. Simulate all the ways that could have turned out then, if that were true. Okay, well, these could have flopped and these could have flopped. Now what's the difference? Okay, these could have flopped and this one and this one and this one. Now what could happen? Oh, now these 3 flopped. So basically, we go through a bunch of simulations and we randomly flip these. We just flip them. We flip each row randomly. And then we see what length difference we could have observed. That's all the ways that it could have happened under random chance. We'll do 10,000 of them. We'll get a pretty good idea. And we'll see, hey, does what we actually observe look different than if our data were just totally random? So here's what that might look like. Let's say on one of my simulations, I flipped a coin and it happened that 2, 3, 5, 8, 10, 12, and 13, I flipped their data. Now I recompute the mean difference in length. Now the next time, a couple different fish flip. But I'm not making any assumptions about distributions. I'm just saying, okay, if there is no difference between day 1 and day 7, how could my data have turned out? If there is no difference in salary between UCLA and USC, how could my data have turned out? That's all we've been doing. What's the opposite of your hypothesis? Do it 10,000 times and see if it's true. So what's your actual hypothesis? Nope, you just got lucky with your data. What's the distribution of lucky? How could it have turned out? If you just do those 3 things in a row, you have your permutation test for any statistic you want to calculate. I hypothesize this. here's the opposite of that. Here's 10,000 ways that could have looked. Simulate it. So we don't need, I think this is probably not going to help, but you can, here's the flow chart. If you're sort of more diagrammatic, this is literally what we're doing. Take our data, flip them randomly. And they have your permuted data, take the means of differences, store them, just do this a whole bunch of times and now compare to what you actually saw. You've seen there's a theme. We just do this over and over again with different statistics, and you've learned all the things now. Now I'm just going to show you different examples of how it shows up. So pull up the paired data example code, which is unpaired, to sample paired.rmd, this one. I commented out all these libraries, so there shouldn't be any dependencies. So what I'm going to do here, and if you want to run it, again, you got to change the CSV path to what you had before, but I'm going to use the same salary, and conveniently there's 70 of both USC and UCLA salaries. And the change is that instead of treating them like they're 70 different professors or employees, we're now going to say, you know what, it's actually the same employees who happen to have worked at both universities. And that lets us control for things like experience, for their just general competency, and look if given that, do we see a change? Now we have more information, right? That's actually going to help us. So if you run it, I think it's with the mean. Where do we leave it at? Mean or median? Mean. All right. So this is the same thing. We took our data, we subtracted it, we took the mean. That's the actual effect. Hey, no, you're good. And for this one, just literally nothing has changed before, other than instead of shuffling the data, I'm doing it slightly differently. Remember, we're just flipping the rows. So each row, each time there's a simulation, I go through and I flip a whole bunch of salaries, and then I take that data and I calculate the mean. And then I go through again and I randomly flip a bunch of salaries, because that's what could have happened if the null hypothesis was true. Given the data, it's just total random chance. And I get a big distribution here of them. And then all I do is look at them and see how my data compare. So now let's look at it. Is everyone clear so far that we're running the same thing, but just instead of shuffling all the data, we now know that some data are linked, and for any link, we just swap the pairs. We know more information. I know that somebody who made 250 grand at USC shouldn't be swapped with someone who only made 30 grand at UCLA. Because I didn't have the information before, but now that I know that, she'll only be swapped with the salary that was maybe 200 grand at UCLA. So there's actually a smaller change. And so you get generally the same stuff, but now I find that my null distribution, let's see, observed effect is 22. Why is it 22? We have median in here. Okay. All right, magnitude, great. So here we go. So this is the bootstraps and just null distribution. Here we go. So now, given the same data, now that I told you they were paired, have you noticed the p-value went way down? This is just using a difference in means. So before, when we did it and we didn't know the data were linked, it was 0.01, 7 or something. And now that I know the data are paired, the p-value went down, even lower. So you want paired data. Because basically what happened is look, if you look at the salary difference, it's still the same. We now know that what could have happened due to random chance is lower, because we know what people's starting salary was, and it's not like it actually changed that much in real life. I might be a little technical, so you can ignore it if you want, but walk away with paired data are linked samples. You want to pair your data. You can't do it in some designs because you sacrifice the mouse, or you do things that are irreversible to the organism. When we do it in brain scanning, usually we don't do that, so we just randomize the order. We'll have them do this task and then do another task and measure both, and then half the time we'll just swap the order in which that happens. So you're controlling for anything that happens due to order. So if that's a possibility, that's a good way to link your data. Like I might have someone do a memory task and then do a visual perception task. And so I want 2 data points and they're linked. Maybe there's a relationship between that, but maybe the memory biases the visual tasks. So on half the subjects I do it this way, and half the subjects I do it this way. So half the subjects will get one condition before the other. So that's one way to characterize it. You just reverse the order. But if you're sacrificing an animal, you can't do that. No going back. Maybe you can create a clone. Clear on paired data. So you have the file. Same thing. We just did exactly the same thing. We went through, we got our samples, we looked at the effect size, and what you'll end up finding is basically just that you want paired data, and everything else stays pretty much the same. So that's a cool way to do it. You don't have to look for repeated measures, tests for your particular statistic of interest. This is a repeated measures, is paired data, same thing. We got a lot to cover, so I'm going to move on unless somebody has a question about this. But I just want you to see the results, which is exact same data, difference in means, 2 orders of magnitude more significant. Because what I did is I looked at the data and I literally just added some random value to each point to create the USC data. So they are paired, so there's a strong effect. All right. Let's talk about correlation and regression. We do this a lot. Y'all seen this? Anscombe's quartet. This is why you have to choose the right metric for your data, and that you can't just plug and play formulas, or you can, but hopefully one day you get caught for obscuring your data. But these are all data that have exactly the same correlation coefficient. It's just the math. You plug any data into the formula, you'll get an answer. So which one of these is, which, if any of these are allowed and appropriate and valid? Yeah, perfect. The first one. Anything else? What's that? Lower left, does that seem okay? Which one? Does anyone know the assumptions behind the math that literally leads to the derivation of correlation and coefficient? I'll give you a hint. Here's not to do it. If this happens in real life, so this I like to go around and take pictures at conferences, especially doctor conferences, because they don't get a formal training in stats enough, like y'all are getting. Here's one. Why isn't the Tyrannosaurus Rex? Why isn't this correlation valid? Because of the Tyrannosaurus of exponent and log of body mass. Why not? Just, you don't have to know the rules. What is it? You're just a scientist. What seems funny? Okay, yep. Log scale is valid. If you want to do log, you can. Should have a reason. Hopefully they satisfied it. You can't just log. If you transform variables enough, you'll definitely find something. Yeah. Yeah. Do you think it's does it look non-linear to you? Oh yeah, yeah. You can transform things though. That's okay. It's okay. Once the requirements are that once you're in your final data set for the math to work, you have to have a linear effect. But you're welcome to train. Units are just units. However you collect them, you could transform them to something else. It's not illegal. It's just suspicious. So why? Come on, you're scientists, or some of you are scientists. Why, if you looked at this graph, would you or would you not believe it? I guess I gave away the punchline. I don't believe it. Do you believe it? No, why not? What's your intuition?
Tyrannosaurus is like a huge outlier. And like
Huge outlier.
data points are clustered together.
Yeah. We actually, look, if people are denying your intuitions, the start of all of this is intuition. You look at stuff, you use your visual system, like something doesn't feel right, and then statistics is just formalizing that. Like we all have our intuitions about why or why not to believe it, and then we just are like, oh, well, we should do t-tests and p-values because that'll quantify there's a huge difference between these groups. Whatever. You don't need that to convince you. There was science before statistics. It works. this is an outlier, and that is not valid. What's wrong with this one and this one? Same thing? These are all from papers. Kidney International. Because they're out, because the way that the correlation coefficient is calculated is because it uses calculus, is a difference in a point from the line squared. So when you have an outlier, the line better come pretty close to that outlier. It's a huge penalty, and the equation doesn't like that. So it'll make sure it goes through an outlier. Some people use absolute value now because we can do permutations and not this crap. But you know, whatever. Here it is. People like it. Outlier, outlier, outlier. If you put it into the formula, you technically still get a result, but it's not valid because there are assumptions on using the correlation coefficient, such as that your data are normally distributed. Shocking to hear that one again. That the variances are uniform across the entire scale, so that do you have an example of that? That's called homoscedasticity, and that just means that on one end all the data points aren't close together, and on the other end they're really, really spread apart. So the spread of the points, let's say, should be pretty much standard across all of them. So that's what you can see here. It's all pretty much standard there. It's all pretty normally distributed. Clearly an outlier. An outlier, not obviously nonlinear. It's a linear correlation coefficient. It only applies to linear data. You can put it in and you will get a result, but it will not be valid. So not obviously nonlinear by eye, because you don't really know. If you zoom out, lots of things are nonlinear. The effect of a protein on cell function is linear over some region, but it's sort of sigmoidal overall, right? So it matters. It's pretty close. And then no autocorrelation means your samples are independent. So you can't take you can't take the hourly data from the stock market and show correlation, because one price is like obviously linked to the price 5 seconds ago. They're not independent. You have a really high correlation, but you can't tell anything about the stock. So only independent samples count towards your power. Those are the 5 rules. We're not going to get to break any of them, but you should know it. And then with the bootstrap, you're going to be able to see how confident you should be in your correlation. So, and I want to bring this up. So do you guys know about Spearman's correlation? The Spearman's correlation is cool. It just says, I don't care if it's linear. I just care if it does increase in one variable lead to an increase in another one. We call that monotonicity, or being monotonic. That's perfectly correlated Spearman style, but not Pearson style. Pearson is the linear one. You can just look it up. There's 2. It's not as popular because the stats aren't as nice, but now we don't care. Now we're not limited. So I use this all the time now because lots of things are nonlinear that you play with. And you can either transform the data and do that, but it still won't necessarily be linear, or you can just use a more flexible coefficient. So I like Spearman's correlation. They're close, they're related. So, any questions on correlation coefficient? Well, let's say that we just want to measure the correlation between day 1 and day 7 among fish. And we have a particular, so now we have paired data again. So correlations are fundamentally paired, right? Because think about it, it's one variable and another variable, and each point is linked. The observation in serum phosphorus is linked with particular aortic calcium content. That's what the sample had both attributes. Yes? Correlation data, we call it bivariate. There are 2 variables and they're linked. So here's how we might do it. So let's say, again, I'm reviewer 3 and I'm skeptical of your paper. And I get that when you actually just correlate these values, you get a really high correlation, that an increase in length on day 1 is correlated with an increase in length on day 7. Big fish get bigger. Didn't have to be that way. But okay, looks like a pretty clear correlation that day 1 is related to day 7. What if I said, nah, I think it's just random chance? So your hypothesis is there's a correlation. Because it didn't have, right, it could really be that fish that started off big on day 1 already reached their maximum and were likely not to grow. And small fish were likely to grow. So you wouldn't necessarily have to see a correlation here. And you say there is one, and I say, okay, well, prove it. So what's your hypothesis here? Stated as a correlation. You will learn the most if you put yourself on the line. You're writing a grant, and your formal hypothesis is what? The numbers? You don't, no numbers needed. What do you mean by numbers?
Oh, no, because I guess the question was like,
Just like out loud, what's your hypothesis?
is that the day one values are correlated?
Perfect. Exactly right. So formally stated, we hypothesize that there is a correlation between length on day 1 and length on day 7. We hypothesize there is a correlation between the number of times you vape and your likelihood of getting lung cancer. Increase in one leads to an increase in another. We hypothesize that, right, we have to put our hypothesis out loud. So what's the opposite of that hypothesis? That there's no correlation between length on day 1 and length on day 7. How many ways, okay, well, what could that look like? How many different ways could that show up? And how could you do it? What's one way that the data, if there was really no correlation, how else could the data have turned out? Yeah. What do you shuffle or flip? If I were to say there's really no, give me one other way the data could have turned out. Yeah. Beautiful. If I just took all my day 7 values and I just shuffled them, I would break the link that I hypothesize is there. Right? It's slightly different than the paired data before where like, look, I didn't lose track of my records. I'm cleared fish 1 had both these links. Now we're saying something different, which is, I get that all these observations happened on day 7 and that there's a difference. I just don't agree that this one had to end up with this one. This one could have ended up here. This length could have ended up here. Your hypothesis is that there is a link between each of these things and the way they showed up together matters. So the opposite of that is just like, well, shuffle them all. And that's important to take home. There's a difference between having a mean effect and a correlation. You could say that the fish are generally bigger on day 7. It doesn't mean that the bigger fish had to get bigger. Could have been that the smaller fish got more food because they look smaller and usurped them. Whatever. But it's important to walk away with the difference that when you have two data like this, there could be a mean difference and there could be a correlation and they're not related. It could be, for example, that if you vape at all, even one time, you get cancer, more likely. But that doesn't mean that there would be no correlation, right? No matter how many times you vape, it would have no additional effect on you getting cancer. So there's no correlation, but there is a mean effect that, yeah, vaping is associated with more cancer, but it's not for each pair that it matters. So if that were the case, that's, you know, now that we sort of got that, you can see why shuffling matters. It's like, okay, here's the length I got on day 7. I'm clear about that. It just was random chance that this one ended up with this one. It could end up here or here. I would still have a mean difference between day 7 and day 1, but there wouldn't be a correlation. Or there might be, but it would be smaller. Alex.
This is connected to your slope for your regression, right?
Mm-hmm.
They're all doubling in weight.
Yep.
So flip them, then you're breaking that ability of the double.
Exactly. So you're basically taking your data, and we'll go over the example in our studio. But it's, you know, this is an important point that you might not have thought about before, so it takes a little bit to digest it, but just the difference between a mean effect and a correlation. I hope the vaping example makes it clear that vaping can cause cancer, but more vaping doesn't cause more cancer. So again, when we say like, is it real? It's the annoying part about statistics is being very specific about what you mean. Well, I mean, is it real? Like, is there a monotonic relationship as measured by the linear correlation coefficient? Like, it's that annoying. No one you tell will remember that, but you'll know, and your reviewers will know. So, final time I'll say it, but when you have paired data and you want to measure the effect between day 1 and day 7, you flipped it this way. So you're basically shuffling across whatever you think your effect was. I think there's an effect between 1 and 7. Okay, shuffle that way. I think there's an effect on each fish had a particular weight. linked with the one on the next day for a reason. Okay, well then break the links that way. And if you can, and then we'll learn tomorrow as you can generalize this to many groups and ANOVAs and things. So open up RStudio, open up the salaries correlation.rmd. Shockingly, we're going to use exactly the same data, so you can change it if you want. But, you know, we're actually going to end at 3 today, so we're going to go a little bit faster. But I'll walk you through the, I think it's better when I walk you through the answer first and then how I got there. Let's try that. So here's what I got. So again, you should expect this. And on average, if I shuffle a bunch of data and call correlation coefficient, most of the time, most likely I get 0. No correlation, right? You take a bunch of random points and you correlate them. It's mostly 0, but it's usually never exactly equal to 0 because there's just noise. So sometimes I got a correlation coefficient as big as 0.4, even though I scrambled the data. So that's what could have happened due to random chance. It's not very likely, but it happened. And sometimes I got a negative correlation coefficient. And so we're looking at the correlation between USC salaries and UCLA salaries. And I know the real value. So when I get the real value, the real correlation is 0.59. You just calculate it, right? I call right here. Here's the line. First thing I do, my actual observed, I saw it. My test statistic is on calling correlation between salaries is 0.69. Now the question again was, how likely could that have actually happened by chance? So to do that, 10,000 resamples, we take our data, and all I'm doing here is I'm just shuffling it. So shuffle my USC salaries, shuffle them all, and shuffle the UCLA one. So I broke the link. So the professors who got both those salaries, now those numbers got scrambled. And then I calculate my correlation again. And that's and each time I put it in a little bucket right here and store it. So my 10,000 times, each time I get a slightly different correlation using the Spearman correlation. And then I do just what I did before. And it's so insignificant that the p-value actually was 0.69 is all the way out here. So it's highly significant. And what's great about this is that we've seen the code below is now we can start to put, okay, so now I would walk away with this and say there was a significant difference in in salaries as measured by correlation coefficient between USC and UCLA. Or maybe I'd say more simply, the correlation between salaries at USC and UCLA was significantly different from chance. And then I would cite my p-value. That's what we showed, right? The effect's all the way out here, and the chance is there. Very unlikely had to have been done due to random chance. Super unlikely. So that is the significance test. And then you might say, well, okay, well, what's the correlation? Well, it's 0.69. How sure are you? Well, that's when now you bootstrap and your confidence intervals come into play. So I ran exactly the same bootstrap code that we have. We calculate our statistic here in this loop. Each time we resample, we replace for bootstrapping, we resample our data, and then we calculate the correlation on our bootstrap data, and we get something that looks like this. So that's our correlation. But if you ask me to put confidence bounds on it, they're right here. It's 0.77, but it's between 0.56 and 0.88. So now it's that easy. I remember when I put this on my plot with my advisor years and years ago, and he was like, how'd you put a confidence interval on the correlation? He was blown away because nobody does that. Nobody thinks about that. Yeah, it's weird, but it's super easy. You use exactly, I mean, you just co-op the code we've literally already done. And all you do is use the bootstrapping method. You rerun your experiment 10,000 times and you get slightly different correlations each time. It's not normally distributed, so it's not always convenient to work with. There might be a formula for it. I don't even know. It's asymmetrical. Because of how correlations work, it's more likely to be skewed left. So you say, oh, well, I could have overestimated by a lot, but I probably didn't underestimate by very much. That's just the nature of things. Whenever you have a statistic that's bounded by 0 or some other number, it always squishes like this. you don't get a nice clean distribution. It always looks like this. You get the squish because it's limited and bounded. So it doesn't look like a nice clean continuous normal. So you can't apply that stuff. But it's easy. Run it 10,000 times, get a correlation each time, count 95 percentile limits, and they're there. That's the limit. So now you can put correlation coefficient confidence intervals. So this is how you'd report in your paper. Correlation coefficient was 70.77 brackets, these numbers. You can do it with your machine learning prediction. You can do it with the ratio of your fluorescence over a subset of the sample relative to the entire sample, subtracted from baseline, or whatever your fancy metric is. You can just do it and see what pops out. Any questions on correlation coefficients and how we got a null distribution from a permutation test that tells us if it's real or not real, and we got a bootstrap that tells us our magnitude confidence bounds. Well, I don't know. It depends. If you think that's a good confidence interval, then I do. I don't know. Depends how confident you want to be. Sometimes it makes you feel uncomfortable with your data because if you only have 20 samples, your confidence interval is going to be pretty big. But that's good. That lets everybody else know and is honest and says, like, look, here's my best guess, but there's a lot of margin of error on my guess. And that way, when people do meta-analyses, they can pick up that information. Because otherwise, they don't know how to weight your stuff. They do their best. That's why people bother you to report your actual t-statistic and not just your p-value. Yeah, I think I changed it to Spearman in this, or is that, are you gonna ask why they're different?
No, I'm curious. So I'm like reading a paper and they did find this significant correlation between two variables with the correlation coefficient of 0.5.
Yeah.
And there's a question of like how strong the correlation that is, and like how do we interpret that?
Really great question. I would say, unfortunately, the answer is it depends. But like, so for brain imaging data, if I were to find, I mean, imagine what let's say measure your personality, your 5 major axis personality attributes. Some of them are highly correlated with things that you do in life or with each other, maybe 0.8, but you're answering the survey. So it's pretty obvious. Imagine, in that case, if I could find reliably that there was a 10% correlation between how you describe yourself and whether you go commit murder, that would be pretty important, right? That's like, oh my God, we found out this thing that predicts decently highly. The more you score on this, the more likely you are to murder. That's an important correlation, even though it's only 0.1 and small. Whereas if I had my brain data, whereas if I said your height and weight are correlated at 0.8, you're like, yeah, that makes sense. It's pretty obvious in the world that taller people tend to weigh more, and that's just what's true on average. So it really is field dependent. In the case of brain data, like if I could we did this, if I could correlate activation in your anterior cingulate cortex with how empathic you were, that would be huge. That'd be amazing. Oh my God, I read your brain and then I could predict what you were going to do. Spooky almost. So we do get correlations, but they're usually not that high because life's just not that simple. Great question. So yeah, highly field dependent. Or God, if there was a correlation of even 0.1 between vaping and cancer, that would be pretty worrisome, right? That's like, okay, and it was significant, highly significant, even if it was small effects, you might say, all right, well, I don't know what would be interesting. Does anyone know generally what criteria the FDA or somebody uses in order to ban something? Like how strong of an effect do you need in order to say it's bad? Like not everyone who smokes cigarettes gets cancer. Yeah, it's a great question. So field dependent. Some things you're expected to find high correlations. Any other questions on correlation?
When would we report correlation versus reporting difference?
Yeah, great question. Yeah, just sort of depends what your so correlations are better, but it depends on the data you have, and I'll unpack that. Which is Correlations are when you have two sets of continuous variables, or at least one continuous variable that is your independent one. So like degrees of dosage, or number of times that you vape, or amount of, gene variance, or amount of protein as measured in the blood leads to a particular outcome or not. Then you have a whole bunch of points versus you would do a test when you have two distinct groups or distinct groups. This is the vaping group and this is the non-vaping group, and you are glossing over how much they vaped. Or here's the fish on day 7 and day 1, or males and females. The correlation coefficients don't apply. So correlations are when you have continuous data. And the reason it's nice is because you actually have more information. So if I was to take some data and it looked like, I don't know, like this, you'd say, oh, that's a pretty clear correlation. But if I then reduce that into a low and a high group, you basically are losing these small differences on the x-axis. You're putting them all together, and so you're actually losing information and you have less power to make your prediction. So ideally you want continuous variables, because then you get this dose response, and you might find that, I don't know, what if it looked like this in your data, and you never looked at it, and you're like, oh, they're exactly the same. Shit, I got no paper. And really it was just an inversion effect. You get, once the levels get too high, it starts working backwards. Yes?
And I often see like correlation reported with false discovery ratios. Is that different?
Yeah, false discovery rate. We will talk about that tomorrow. Yep, absolutely important. Anything else on correlations that you've always wondered? Okay, great. So moving on. So we got 15 more minutes, so we're going to power through. All right, so we did the correlation example, and now we're going to change it just slightly. It's funny when you click and nothing happens. Does UCLA pay its employees a different amount than Irvine? So that's now my question. So this is the assessment. So let's say, and this is the process of being a scientist, you often have a very general question to start with. But in order to translate to statistics, you have to be super specific about what you're asking. It's like, oh, is it different? Well, what do you mean? So what do I mean here? What would be my statistic of interest here? If you were to translate this, break it down for me. What's the statistic of interest and what's the test? Yeah, that seems reasonable. That's how I would interpret it too. What test would we use here?
In the t-test, it should be independent. I don't know what's something else. It's independent.
You could use a t-test as long as your data are normally distributed, which they're not. You could take a log of it then. You could try and normalize it. Mm-hmm. Yep. How would you do it? Yeah, so if it was the median, what would you do? How would I test if the median is different between groups A and groups B? Permutation test. Yep. If you want to find out if something's real, by the way, it's good to struggle. Struggle, it means you're more likely to remember it. Permutation test to see if there's a significant difference. Always start with that. Permutation test. Start. So what you're granularly asking in statistics is there a difference between the mean salary at UCLA and USC? And to implement that, you would do a permutation test. And then you just have to settle if the data are paired or not paired, so you shuffle the right way. But otherwise, that's it. So have at it. So find the right R markdown file from what we've learned and figure out if UCLA pays its employees a different amount than Irvine. I'll give you 2 minutes. Just note that I mentioned Irvine. You can code it all by hand if you want, but I do have an RMD file that is very close to what you want to do. Yes, so the original data, maybe I didn't do a good job pointing that out. So the original data, let's just go through it. Let's say it's the unpaired permutation test. If you read in the original data, then there is Irvine. Irvine has they're in the data set. It's a third school. So let's pull up the two samples. Let's just go through it. I think I wanted you to just struggle with it just a little bit. So here's my data. And what I'm pointing out here, when I look at this data, just read it in. So I'm manually, don't do this, I'm manually doing it so that I can look at the variable. So if I look at salaries, I have UCLA, USC, and then I have Irvine. What do you notice about Irvine? The communists. They pay everybody the same amount. I wonder how that might affect the test that we're doing. So what happens is if you knit these data together, we got our original example, which is USC versus UCLA. And I just did a simple comparison. And we did the permutation test between two different things. And so here is UCLA and Irvine. So here's the salaries for the permutations. This is my boo-boo. I forgot I'd actually already switched these and saved them. So salaries for perms. Yeah, I already saved them. Sorry. So what we did before was the difference between Irvine and UCLA. Sorry, I changed this from class to class. So yeah, so there is an answer. It's a $22,000 difference between Irvine and UCLA. Remember what it was between USC and UCLA? 16. It was 16. So it was actually a larger difference. And not shockingly, we have a very extreme p-value. Okay. Now, say, well, that was pointless. Why'd you do that? Well, now I have a slightly different hypothesis about the differences between school. I hypothesize that UCLA and Irvine salaries are linearly correlated. Is that true at a 5% significance level? Do we get what I'm asking? What kind of test would you use here? What's that?
Correlation.
Yeah, use a correlation. And what method, which resampling method would you use? Test if something's real. Remember, there's only two kinds, bootstraps and permutations. And all you're changing between them is just what your statistic of interest is. Means, medians, correlations. So which one are you going to use to answer this question? I got one silent answer. Any other ones? Yeah? 3 silent answers. You guys are rolling. Who wants to give me an out loud answer? Bootstrap would be for putting the confidence intervals on how big of a correlation it is. You want the permutation test to say if it's real or not. So always with these questions, when you say I hypothesize, permutation test. Because the rest is quantifying uncertainty, but there's no hypothesis there. It's just, this is what I saw, and it's pretty sure it's between here and here. Best guess. So we open up, open your correlation coefficient RMD file that we just worked on, and simply swap out the salaries so you get a little more familiar with the coding. Swap it out. Instead of being from USC and UCLA, we want to do it between Irvine and UCLA. So where is that? Over here. Irvine. Okay, this is where's my test? Salaries, correlation. I load my data. I format the data all right here and get all these nice names. So instead of correlating USC and UCLA, I might simply correlate Irvine and UCLA. And here, instead of USC, I do Irvine. I've changed it a few places. So this is more just getting used to what I'm actually doing, which is I'm changing the correlation to be between the appropriate schools. And then when I do my bootstraps, I got to make sure to do the same thing. Now I'm taking my USC salaries and I'm shuffling that whole column. And then I'm taking my Irvine salaries and I'm shuffling that whole column. So there's no longer any matching between a professor at one university and another. So the correlation should be scrambled. They should be 0. But the question is our effect bigger than chance? So now if I knit this together, hey, no errors. That's the best part about it. If you ask a question, we can just test it. I don't have to, it'll take a while to look it up. All right, so let's look. Observed effect, hold on. Okay. Correlation of Irvine and UCLA. I did it again down here. Irvine. So when you write your code, it's nice to have one function for everything. But I don't do it so that you guys can see everything I do. Okay, so let's do this again. Okay, so here's what I see. My correlation coefficient, my best guess is still 0 because right, this is just random chance. Here's my null distribution I built. Most of the time, most likely 0, but I could observe a correlation of 0.4 just due to random chance. And that's what everything, all the t-tests, whatever, all this is happening behind the scenes. It's the same thing. They're just building it for you. And then you're comparing my actual observation, which is right here. The actual observation I got was slightly negative, and I got no, my p-value was not significant. It was 0.43. So the correlation between Irvine and UCLA salaries was not significantly different from chance, as we can see here. And if you just look at the raw size of it, it was tiny. 0.08, it basically wasn't even real. Probably just 0. So what happened? How come my answers were so different? Here's the answer. There's no, can we see with our eyeballs, there's no difference between USC and Irvine in terms of correlation? There's no correlation between the two. But remember the answer to the first question. Did they pay a different salary and was that significant? Yeah, that's $22,000 salary difference and it was 0.001 p-value. So what this is trying to unpack for you guys is there's a difference between, again, a mean effect, because Irvine pays more, but there was no correlation. Just because you made more at one university doesn't mean you make more at the other one. So they're fundamentally different questions, and that's why the paired test was flopping one way and the correlation was shuffling the other way, because you're asking slightly different questions. So when you think about your hypotheses you ask for your experiments, important to keep in mind exactly what you mean. Do you mean more of one means more than the other? Or do you just mean overall there's just a difference? All right, that's the end. Thanks. See you tomorrow. Great. Anything else? I'll have a couple questions, then I gotta go. Stop share, stop recording.